Ninth or the last lecture on AC circuit theory. Today we shall consider parallel resonant circuit. A parallel resonant circuit is a parallel combination of a real inductor, of which is a pure inductor of inductance L plus a small series resistance RL, and a real capacitor, which is a real capacitor is a pure capacitor C plus a series resistance. So this is the parallel resonant circuit. If we consider the circuit, this combination is fed by an AC voltage source, then at a particular instant, if V be the voltage phasor, the corresponding supply or line current phasor is I, then it splits up into two parts, and the KCL for AC circuit becomes this. If we want to find out IL, the current in the inductive branch, the current in the inductive branch is VL, V the voltage phasor by ZL, which when is written in a, this is equal to V RL plus JXL. This can be written in two ways. One is V phi L, or we can write it V This is the polar form and this is the Cartesian form. Similarly, IC can be written as omega c. The total current I flowing through this we write YV is equal to this is YCV, where Y's are the admittances. So we see that if we compare this relation with this, we see that admittance is just being added up for parallel circuit. So this is basically this plus this, and if we for XL we write this, It is sometimes written as G the conductance minus the susceptance. Earlier we have seen in the case of series resonance circuit that at resonance the current is a maximum and current and voltage are in phase. At that time we reminded that the general definition of resonance is that the effect and cause are in phase. In this circuit, if we consider the applied voltage phasor to be in the F cause, then the current is the effect. So they must be in phase. So if we want that I and V phasor to be in phase, then Y must be a real quantity, that is this part has to be 0. So this is the definition of resonance. We can also write it as mod Y times e to the power minus j theta, where mod Y is g square plus b square and tan of theta is equal to b by g. You know that at omega is equal to omega p, the resonance frequency of the parallel circuit. Tan theta is 0. Theta is 0, and furthermore the y is a minimum. So we write resonance frequency we define is that is omega p is that value of omega for which this part is 0, which leads to omega p square Note that if we were working with pure inductor and pure capacitor, this part becomes 1 and it would be the frequency of the resonant frequency would be 1 upon LC. Omega p is a real quantity, that is this part has to be positive. So if we have or the vice versa, the omega p is negative, so the circuit is never resonant. Circuit never resonant. On the other hand, if we have RL is equal to RC is equal to L by C, the condition is satisfied always and thus the circuit is said to be ever resonant. If we so this is the main thing, and if we fed the circuit by an AC source, then we see that the RMS current, this expression I is equal to YV, where we write Y is equal to mod Y e to the power minus j theta. V, if in terms of RMS values, this would be IRMS is equal to If the circuit be fed by a constant voltage source, is by a constant voltage source, Vrms is a fixed, so the I will pass through a minimum at the resonance frequency, because Y is a minimum at resonance. So we write and this is the value of this value is related to real part of Y at the resonance. Let me come to the vector diagram, phasor diagram corresponding to this situation. Let at a particular phasor diagram, at a particular instant, this is be the V phasor. This is the V phasor. Now, this V phasor is applicable to both L and C. So we know that if this is be the case, then VL will this is the VL phasor, and so this is the V phasor, and this is also the current direction of the IL phasor. But here the reference V is this, so we are to this angle is phi L, so we are to rotate this. So if we want to make P in this direction, then IL is in direction. So if I current be passed through this series combination, then this is the phasor diagram for this part, and this is the V phasor, but we have applied a reference voltage phasor, so we rotated this entire phasor diagram by the angle phi L, so that V coincides with the horizontal line. So this is the IL phasor. Similarly, for IC phasor, we see this is the PRC phasor, and this is also the IC phasor, and this is VC phasor. This is the V phasor, and this is phi C, and we are to rotate this second. So actually we will have I phasor will be the vector sum of these two. This is the vector sum of these two. So this is V phasor, this is IC phasor, this is IL phasor. This is IC phasor, this is IL phasor, this is V phasor, so this is the I phasor. We can resolve this we can resolve this IL into two components. One is parallel to V phasor and other one is perpendicular to V phasor, which is called the component of IL in phase with V is called in phase component, which is in this direction, and the out of phase component is directed downward. Similarly, for this, the in phase component is in this direction and out of phase component is in this direction. At resonance, what happens? I becomes parallel to V. I becomes parallel to V. In that is the out of phase components, out of phase components of VL and VC are equal in magnitude and they cancels up, and only the in phase components of I survives. So this is a phasor diagram approach. One thing is that if we want to use real capacitor and inductor, it is found that it is possible to have a good quality of capacitor. For a good, in reality, it is achievable. That is for which RC is very small. RC is very small, so the original edge for a real capacitor, for a good capacitor, so the resonance frequency this part is 0, so this is a simplified version of this. If we find out the current, the line current at resonance, and the line current at resonance, so IP at resonance is YPV in terms of the phasor, where YP is equal to real part of Y at omega p, and which is found to be this. This is called this is also called 1 by RD, the dynamic resistance. RD is the dynamic resistance. So if we are working with a good quality of capacitor, then in terms of RMS values, this will be the minimum value of IP, and the corresponding Y is related to the dynamic resistance. And now come to the RMS value of current, RMS IP, IRMS at resonance. So this is simply this is and PCRMS at resonance is simply IC is for a good quality of capacitor, it will be this expression, this part is 0, this part is 0, so this is simply j omega c, and so far the RMS value is concerned, j will not be there, and at resonance omega is equal to omega p, so it is omega p c VRMS. We define the voltage magnification factor we define voltage magnification as PIC at omega is equal to IRMS omega by ICRMS at omega, and GIC at omega p, this becomes ICRMS at resonance by IRMS at resonance. So this quantity, if we apply this is omega pc, and in the numerator VRMS gets cancelled. This is the Q factor. It is the Q factor of the circuit. That is the voltage gain, the current gain at the resonance is the Q factor. Similar definition could also be applied to the series resonance circuit, whose Q factor can be defined for series resonance circuit. Q factor is in terms of RMS VLRMS at resonance by VRMS at resonance, or it could be for C also. It can be shown that for parallel resonance circuit with high Q, this is also approximately equal to GIL at omega p. So if we were working with a good quality of capacitor, one thing is to be noted that the phasor diagram is changed a bit. So let me have a comparison of the phasor diagram. The phasor diagram is that this is IC phasor, this is IL phasor, and then we add up these two to get I phasor. This is for real capacitor with RC not equal to 0. If we were working with a ideal capacitor, then this is IC, this is IL. This is the change of phasor diagram. So this is I. This is with RC is equal to 0, so that IC is perpendicular, just perpendicular. These are the changes. And by this we end our discussion on alternating current theory, as well as it completes the course on current electricity of semester 2 students.